Hello everybody and welcome to the last unit in our course in Introduction to Logic. In this unit we're going to cover conditional proof and indirect proof as we use them in predicate logic. There really isn't any information in this unit. We're only going to put together all of the skills that we've been working on ever since we introduced propositional logic and moved on to predicate logic later on. So I'll just show you a few demonstrations and walk you through the steps in the proofs that I'm taking. Let's first look at how we can use conditional proof in predicate logic. There really are two possibilities. We may be given a conditional sentence that contains two individually quantified sentences, one is in its antecedent and one in its consequent. If that's the case, we are going to assume the entire antecedent and try to derive the entire consequent. Alternatively, we may have a conditional which is quantified in its entirety, and that's the case we're given here. So when we work with quantified sentences like that, we are going to use the subproof to derive the conditional and introduce the quantifier by generalization afterwards. Now, it is important to remember that if we are going to be using universal generalization to that conditional, we better be working with variables. If we are going to only be generalizing existentially, it wouldn't really matter whether we're working with constants or variables. So with that reminder, let's just assume an AX sentence here, and remember that that's going to restrict the steps that are following on the basis of that assumption, and we designate that by the indented line in our subproof. Now we are going to introduce yet another restriction here, and that's going to be the restriction of not being able to use universal generalization within a proof if we are trying to generalize to a variable that appears as an unbound variable in the assumption. In other words, with our assumption here of AX, we're not allowed to use universal generalization to the variable x within this subproof. Now, we are going to eventually use universal generalization, but that is going to be outside of the scope of this proof, so that's not going to affect our final result. We are allowed to use the variable for existential generalization, however, and that's exactly what we are actually going to do in this case. Now, let's look at our premises and see our backward strategy to derive the conclusion we're trying to derive. So we are trying to derive EX on the basis of the assumption of AX. Now we see that we have an E sentence on line 2. It appears as a consequent of a conditional there, which means that if we eliminate the antecedent of that conditional, we will be able to obtain an EX sentence out of there. So then next question is, how do we obtain the antecedent of line 2? We see that that's a quantified sentence that is actually a disjunction. So if we could derive one of the disjuncts there, we could add the other one and then apply existential generalization. So let's see what we have on line 1. We see we do have a C sentence there, but it appears within the consequent of a conditional, which means that we are trying to first eliminate the antecedent of that conditional. And we see that that's an A sentence, which is existentially quantified, and we could obtain that from line 3 on the basis of existential generalization. With line 4 and 1, we're now in a position to derive for some x, bx, and cx, and now are in a position to instantiate existentially and get the sentence BA and CA. Just a reminder, if we are applying existential instantiation, we are restricted to only using a constant for that instantiation. Moreover, that constant has to be such that it doesn't appear in the proof already. We don't have any constants here, so we could have used any one whatsoever. I just randomly picked A. And now let's focus on deriving C from that line. Now, it is a conjunction, so we could get it by simplification, but remember, in the system we're using, we need to first apply commutativity and then simplification in order to obtain the C sentence. With this line, now we're in a position to add D sentence to that C sentence, and now we're in a position to generalize existentially and obtain the antecedent of the conditional in line 2. With this step, we're then in a position to derive for any x ex by 2, 10, and mod exponents. Now remember, I'm trying to get to an ex sentence, but it shouldn't be quantified. Now, given that this is a universally quantified sentence, I am allowed to instantiate to whatever variable or constant I need here. And in our situation, I need the variable x, so I'll just instantiate to ex. Now I'm in a position to discharge my assumption, and that will give me the conditional sentence I was trying to derive. And now last step is reintroducing the quantifier by universal generalization.